Welcome to the EE Smarts Lesson Energy Roller Coaster. Watch the portion of the video I'm going to show you. Think about what you are seeing. Have you ever been on a roller coaster? What does it feel like? Think back to the last time you were on one, if you've ever ridden one. What happened to the car as it climbed to the top of the first hill? You may remember the car got slower and slower as it climbed to the top of that very first hill. What happened to the car when it reached the top of the hill? Well, it stopped momentarily, like a split second, when it reached the top. Then what happened to the car as it rolled over the crest of the first hill? Well, it swooped down that hill at breakneck speed as it rolled over the crest of the hill and down that first long slope. Potential energy is stored energy, and kinetic energy is energy of motion. On a roller coaster, when is the potential energy the greatest? Well, when the car reaches the crest of the very first hill and almost comes to a stop just before rolling downward, it's at its greatest potential energy or stored energy. On a roller coaster, when is the kinetic energy the greatest? Well, when the car goes over that first hill and it starts to move, the potential energy is transformed into kinetic energy, and it reaches its greatest kinetic energy at the bottom of the first hill while it's moving at its fastest speed. Look at the two pictures of roller coasters. Which one shows greater potential energy? The picture on the left shows greater potential energy because the car is at the top of the first hill before it begins its descent. That's when the potential energy is the greatest, or the stored energy is the greatest. Which picture shows greater kinetic energy? Well, the picture on the right shows greater kinetic energy because the car is moving down the first large hill. The kinetic energy will actually be at the greatest when the car reaches the bottom of the first hill, when it's at its fastest speed of the ride. The materials needed for the activity I'm going to do are string, tape, and washers of different sizes. I'm going to perform two sets of tests. For the first test, I will change the length of the string but keep the washer the same. What do you think will happen to the number of complete oscillations? That means a full back and forth in 15 seconds as the length of the string is increased. Will there be more as the string increases? Will there be less? Or will there be the same number of complete oscillations? For the second test, I will change the size of the washer, but keep the length of the string the same. What do you think will happen to the number of complete oscillations in 15 seconds this time as the size of the washer is increased? Will there be more each time? Will there be less? Or will there be the same number? Let's see what happens. For these activities, I have the following materials. I have string, tape, and washers, and I have different size washers. For this first activity, however, the washers are all the same size because that is one thing that I'm keeping constant. The length of the string, however, is different for all three because that is the variable that's being tested. So when you see these washers hanging from a string like this, they're making a model like a pendulum because they can swing freely, like a pendulum can. All right, I'm going to move these two to the side for a moment, or to the top here, and demonstrate to you how this is going to work. I'm going to hold the
washer, even with the countertop, and I'm going to release it. And when I release it, I'm also setting a timer for 15 seconds. And I'm going to count the number of complete oscillations that it can do in that time period. So for a complete oscillation is a forward and back. So here we go. This would be 1. That's 1. So every time it comes to me, 1, 2, 3, 4. You get the idea? That's how we're going to test them. Now, what do you think is going to happen with the 3 different length strings? Will the number of oscillations be the same? Will they be different? Will it get more oscillations as the string gets longer, or will there be less oscillations as the string gets longer? We're going to test it and find out. So here we go. I'm going to set this and set a timer at the same time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, 14 complete oscillations. Now I'm going to do that test 2 more times when I'm off camera so that we have 3 trials that I'll then make an average of for to help with accuracy, because there's always human error involved and things don't always go exactly as you would like them to. All right, so here we go with the second side, the second length string, the 45 centimeters. I'm going to do the same thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so that was 11 that time. Now I'm going to do a third one with the longest string. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that did 9 complete oscillations in that 15 seconds. So as you saw, the frequency or the number of oscillations in a given time actually goes down as the length of the string gets longer. Now we're going to look at a duo test of 3 different size washers, but all the same length string. Okay? So we have a small, a medium, and a large. And I'm going to start with the small one and do the same thing. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, that was 13 and a half because it was halfway through that 13th oscillation when the bell went off, when the timer went off. Here's the next size. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Again, 13 and a half. And then the final one. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Again, we had just about 13, 13 and a half. So the size of the washer didn't make a difference. Did that surprise you? Well, let's talk about this in a few minutes.
All right, look at the data in the table. Do you see any patterns? You may notice that when testing different lengths of string. As the length of the string increased, the number of oscillations decreased. Were you surprised by that? Why do you think that happened? You may notice that when testing the different size washers, as the washer size increased, the number of oscillations remained the same. Were you surprised by this? In the data chart, you see all 3 trials that I did and the averages. Now let's look at a graph of the averages. And it clearly shows a decrease in the number of complete oscillations as the string length is increased. Why is this? Well, think about it. The force acting on the washer is gravity, which is constant. When the string is longer, the washer has to fall farther, traveling a longer distance, which takes more time. The time it takes for the washer to make one complete oscillation or back and forth is called a period, and the number of oscillations in a given time is the frequency. So as the string gets longer, the distance the washer falls is greater, the period is longer. That means that there are fewer oscillations in a given time. In other words, the frequency is less. When using the same length string but different size washers, you can see that there was no significant difference in the number of oscillations. Why is this? Again, the force acting on the washers is gravity, which is constant no matter the size of the mass. With the strings all the same length, each washer has the same distance to fall, and therefore a complete oscillation has the same length period. As a result, the same or almost the same number of oscillations takes place for each size washer in the same time frame. Think back to the roller coaster. When was the potential energy at its greatest? Do you remember when the kinetic energy was at its greatest? Well, look at the diagram on the table with the washer swinging from it. Where is the potential energy here the greatest? The answer is at point A. Just as the roller coaster had the greatest potential energy as it reached the crest of the first hill, the washer has the greatest potential energy just before it's released the first time. It's at its highest point here. When in the diagram is the kinetic energy the greatest? The answer is at point C. Just as the roller coaster had the greatest kinetic energy as it began its descent and reached the bottom of the first hill, the washer demonstrates the most kinetic energy when its swing reaches the bottom the first time. Between A and C at point B, you are having a change of potential energy to kinetic energy. And then when C goes to D, the change goes the other way. It goes from kinetic energy to potential energy. And so the energy transformation between kinetic and potential is pretty continuous here. However, it is at its greatest potential energy at A and its greatest kinetic energy at C. So thank you for going through the EE Smarts Energy Roller Coaster lesson with me.